Hey everybody, my name is Jeff Koss, and this is my presentation for a project that I had to do in a robotics class at the University of Advancing Technology. Robotics 211 is the name of the class, and the project I had to do was I had to write code and implement it to control a DC motor. So what we had to do is we had to use pulse width modulation on an AVR chip. I'm using the 328P. It is hooked up to an Adreno, but only for power source reasons. I'm actually programming this using Microchip Studio, and I'm programming it directly to the AVR chip itself using straight up C, you know, and we're using the libraries that come with the AVR, not the Adreno. Um, so this was pretty cool. I liked it. I loved this assignment actually. So what I had to do here's what I did here. So um, this is going to be a little complicated to explain, but it's actually really simpler than what it looks like once you get the hang of it. It took me a little bit to get the hang of pulse width modulation and interrupts and timers and stuff like that because it was a different form of programming than straight up like C++ or something like the Adreno or something like that. With this, with a microchip, we're dealing with registers, and we're dealing with little tiny chunks of memory that are bits that make up bytes, and you have to manipulate those bits individually. And when you do that, it produces different things. So it could tell a timer that if you go above this number to reset or something like that. And once you have that concept in your mind and you know the syntax, it's a lot easier than actually programming with something like the Adreno. And I'm really happy that I'm learning this. So let's get into the nuts and bolts of this. The first thing I do is I define the CPU speed at 16 megahertz, which is 16 million hertz. The reason why I do this is because that's what the internal clock is basically set up on that. I include two header files. The AVR input output, that's pretty much your standard file for your AVR stuff. It's got all the basics in it. I use a delay header file, which allows me to use delay functions. If I wanted to delay it for 10 seconds or what, not. It works. It's under the utility delay header file. I actually use a double float here because we're going to be using this number as a percentile to implement the pulse width modulation basically. And I call it duty cycle. I set it to 0. Then we have our main function, and before we call our main loop, I declare a couple of things. I make sure things are happening. So I have a data direction register. I set it on D, and I set pin D6 on the AVR chip to an output. And the reason why I do that is because that pin is the pin that this chip uses for the overflow control register 0A. And that's the register we're going to be using to determine whether or not we're going to turn the duty cycle on and off. So then we set the TCCR 0A. We set the, this is the, basically what this does. I'll have to bring up the data sheet. Actually, I'm not going to bring up the data sheet. I'm just going to explain it to you. So what these things do in layman's terms is this is going to set this COM 0A1 and this register is going to compare it with the OCR 0A, and that's what we use to compare the two numbers together. The WGM00 and the WGM01 are registers, bits like 1, 0, 1 and 2. And if we set both of those to high, basically, we set our thing into, oops, there's a misspell there, fast pulse width modulation mode, which is really useful. You know, we use it for a lot of things. Then we set the TCCR0B to CS0, 0. We set that to 1. So basically what this says is we're not going to use any pre-scaling. Pre-scaling is basically a number we use to divide it into the clock so we can get more precise control over our clock speeds and fine-tune it basically. Because I'm using an 8-bit clock right now, to be honest with you, it's fine just going up to 255. So in the main loop, here's what we do. I set the duty cycle to 100. We take that number and we put that into the overflow control register 0A. And we tell it to take the duty cycle, divide that by 100. So 100 divided by 100 is what? 0, right? Or 1. 1. If you divide it, it'll be 1. So we times that by 255, we get 255. 255 on a pulse width modulation duty cycle is 100%. It's going to be on. So this is how we turn this thing on at full power, basically. We delay it for 10 seconds. We set the duty cycle to 50. So we say take the duty cycle divided by 100. Okay? So that's going to give us 0.5. We times that by 255 and we get half of 255. Well, half of 255 on this duty cycle is going to be 50% power. So we drop the power down, we drop the power to the motor down to 50%. Then we delay it for 10 seconds. We set the duty cycle to 75. This is genius, man. I love it. So we take that and we put it into the OCR 0A register. We take the duty cycle of 75, divide it by 100. So what do we get? If we times that by 255, we get basically right around 75% of the duty cycle, or 75% power. Right? Math is beautiful when you know how to use it. Okay, so then we delay for 10 seconds. We set the duty cycle to 25. We delay that. We put that in the OCR 0A register. We divide it by 100, and basically 25 divided by 100, we're going to get 0.25. 0.25 times 255 is going to basically give us 25% of 255. 25% duty cycle, 25% power. Delay it for 10 seconds, and we start it all over again. It works. It works great. So there is something else we had to do. I had to use an H-bridge in order to make this work, and here is the schematic. And I'm sorry for my bird being very rude right now, but he's sitting right next to me, and unfortunately there's nothing I can do about that. But moving on, here's a schematic that was done in fritzing. This is a schematic I borrowed from the class that I was in, and I like the way it's done. However, I do a couple of different things. I do not use these two batteries here. Basically what I did is I took the 9-volt, chopped the 2 wires, and I put them into the positive and negative on this side. And then I ran 5 volts from the Uno on this side. And the reason why I do that is because when you're changing duty cycles, if it drops below a certain voltage, it'll run the lower voltages, right? But it won't run the higher voltages because we need to run this at a higher voltage. The motor is going to run at 9 volts. So let's say if we're running at 100% or 75%, we're going to need those 9 volts to power this motor efficiently, right? Otherwise, it's not going to work right. And then when we drop it down to 5 volts, you know, obviously we're using a less duty cycle, less voltage. So, you know, that's why that works. Now, here's what we do. I set this pen here. It goes into the first register because that register is the register that is going to control the input and output for this side of the H bridge. We apply power to this. So this is Y1, and then the yellow one is Y2, and the Y1 and Y2 are basically the outputs for the H bridge, which are going to go into here. How this works is like this. once this pin is set, if this pin is set high and this blue one is set high, the motor's going to run. Okay? If all three are set high, the motor's going to go into a stop mode. And that's how we do it. Basically, we're switching registers on and off to tell it what to do. So this is how we can make, like, if we had a robot, let's say we had two motors. I had one on this side, one on this side. By manipulating those registers, we can make the robot go forward, backward, turn left, or turn right. And we can control the speed and the duration of the turn by, you know, setting interrupts into it and stuff like that, which is amazing. But for this, we just had to demonstrate the motor. So without further ado, I'm going to show you the video I shot with the motor. Hey guys, alright, sorry about the mess here, but this is the pulse width modulation DC motor. Okay, so it's going to start out, we are working at 100% power or 100% duty cycle, which is always on. It's going to stop for a good 10 seconds. And when it resumes, it's going to be at 50% cycle. So there's your 50%. You can see it's running much slower. And that'll continue on for a little bit. It's going to stop for a couple of seconds here, and then it's going to go to 75% power. There it goes, 75%. You can see it's running a lot faster than what it was, a lot stronger. And it stops. And then once it resumes, it's going to go to 25% power. There it is at 25% power. And it stops. And then the cycle repeats. It's going to go back to 100% power and repeat. We'll go for the first few seconds. There you go. As you can see, whoa. As you can see, it's working just fine. Thank you very much, guys. Have a good one.